Hello everyone, welcome to this session. So in this session, we will talk about the working principles of SVM. So let's start from the simplest case, linear SVM, hard margin classifier. Right. So the first concept to introduce is distance. So distance is in SVM is a distance between the point and a hyperplane, right? So mathematically, we can consider is the length of the perpendicular line segment connecting the point and the hyperplane. So let's see two figures. A point xi is here. If it's two-dimensional, hyperplane is a line because the distance is here, right? And three-dimensional, we can see that this is a h2 is a plane, x is here, distance is here, right? So if xi lies on the hyperplane, distance is 0. So if xi lies outside the hyperplane, so we can calculate it by the distance formula. So what is the formula? We can see is here. So this is optional. So we can see the xi is a point, the hyperplane is a w transpose multiply x plus b equals to 0, right? Xi the hyperplane, distance like this. So we can see we want to get the maximum between 0 and this value, because distance we need it to be a positive value. And in the denominator, this is the norm of the w. So we can calculate it like this. So this is the distance, right, for any data point to a hyperplane. So knowing the distance, we can consider the second concept, margin. So how to calculate margin and what is margin? So let's first see a data set. So from xy1 to xn, there are n samples. So x is the input, y is the label. So we can see here. The margin is the minimum distance from each data to the hyperplane, right? So we call it n, wb. So what it is, we can see is here. There are n data, right? Each one we have a distance, and we get the minimum of them. But this one, we call it the margin. The size of the margin, it decides the generalization ability, or we say the confidence of the classifier. So SVM, we want a larger margin or a smaller margin, right? As I said in the last session, we want a large margin, right? So we aim to select the largest margin. Based on this, we get the hyperplane. So for example, in these two figures, we can see there are class positive 1, class minus 1, the same points. And we have two hyperplanes, h1 and h2. So h1 clearly have a larger margin than h2. So this will be selected by the SVM, right? So knowing this, the margin, the concept of this, we can learn how to train the SVM. So in SVM, like many machine learning methods, so learning is we are optimizing something, right? So now we need to find out what we are optimizing. So now for hyperplane, we have the margin, right? So margin is what is the smallest distance, right, between the points to the hyperplane. So we want it to the largest margin. So what we do is to do what? Is we want to maximize the margin, right? So margin is a function of the variable w and b. So the decision variables are w and b, and we want to maximize this function. But there is a constraint. The constraint is what? Because it's hard margin, so all the data points must be correctly classified. So to solve this optimization problem, so mathematically, we can put it like this. So we want to minimize, note that this is minimize, so this objective function, so this is not of w. So this is saying, the constraint is saying, the points should be correctly classified. So from this one, you may have some questions, right? So first of all, why we need to minimize this function? This is equivalent to maximize the margin. This is the first question. And also this is saying the points should be classified correctly. So why only the positive one class is considered? Where is the negative class? -1 class. And also why this is 1 instead of 5, 10. So here I provide a hyperlink to provide you more explanation to this, but this is not required in this specialization. So seeing this, now we have already obtained the optimization problem, so that the learning has been translated to an optimization problem. Then we need to solve it to get the optimal value of the W and B, right? So by the conventional mathematical optimization theory, so this problem it can be solved easily. So later I will show more details in the coming sessions. So considering the linear SVM hard margin classifier, so now I provide you an example. That is a iris flower classification. We have seen this example for quite a few times, right? So this is our feature, the feature vector. We have 4 elements, and the label we have 3 kinds of flowers. There are 150 training data, and here I show the table. Now, if we want to use a linear SVM, the hard margin classifier, we need to make that the data set to be linearly separable. So we choose only 2 features here and here, and we only choose 2 categories of flowers. We can see these are the 2 kinds of flowers here. So using the linear SVM hard margin, this is the result, and we can see this is data 1, data 2, classified. This is a hyperplane. This is the margin boundaries. Support vectors are here, so we can see that, right? So you can try yourself all of this in the live script. So thank you for listening. Bye bye.